On the 89th floor of Taipei 101, on a Saturday in August 2015, a glass of water resting on a restaurant table began to move visibly. The water climbed one side of the glass, fell back, then climbed the other. Folding blinds tapped gently against the window frame. A light fixture suspended from a thin cable moved in a slow, steady rhythm. Outside, Typhoon Soudelor was crossing the island of Taiwan, producing wind gusts of up to 100 miles per hour. From the street, the tower appeared perfectly still. A vertical column of blue-tinted glass rising 1,667 feet into the sky, seemingly indifferent to the storm. But on the upper floors, sensors were recording what the human eye could not see. The top of the building was moving laterally relative to its base. It was not a mistake. It was not a failure. It was exactly the behavior anticipated by the engineers who designed the tower between 1999 and 2004. And this is where the first contradiction appears. A skyscraper that moves looks fragile. A skyscraper that does not move is almost impossible to build. Human intuition tells us that safety and immobility are the same thing. The less it moves, the safer it must be. The stiffer the material, the less it deforms. A building swaying on its upper floors should immediately trigger an internal alarm in anyone watching it. And yet, making a skyscraper completely rigid is not merely impossible, it is undesirable. A perfectly rigid building would require enormous quantities of additional steel and concrete, disproportionately larger foundations, and far more money. And worse, it would concentrate wind forces at localized points within the structure, creating stress peaks at connections, corners, and supports. Absolute rigidity, when engineers can even approximate it, becomes a structural trap. Controlled flexibility, by contrast, is what allows a 1,640-foot building to remain standing under the pressure of typhoons, earthquakes, and constantly shifting winds. That does not mean, however, that the building can simply sway however it wants. Modern engineering treats movement as a problem that must be predicted with millimeter-level precision. Engineers calculate how far the top may move relative to the base, how quickly the oscillation will occur, the natural frequency at which the building vibrates, and how that energy will dissipate over time. There is a structural limit, the point at which steel or concrete would begin to behave dangerously, and there is another limit much closer to everyday conditions, one the public almost always overlooks. The limit of the human body. A tower can be perfectly safe from a structural perspective and still cause nausea, anxiety, and loss of balance among those who work, live, or sleep on its upper floors. Before the wind threatens the building, it threatens the occupant's tolerance, and that is precisely where the engineering of sway becomes far more subtle than it first appears. The first layer of the explanation begins with materials. All structural steel and reinforced concrete deform under load. Absolute rigidity does not exist in nature. A loaded column compresses by a fraction of a millimeter. A beam deflects slightly downward under its own weight. A 1,312-foot tower under wind pressure bends along its vertical axis in a curve that may amount to only a few inches at the top, but is mathematically unavoidable. There is an important distinction between elastic deformation and permanent damage. A metal ruler that bends slightly under the pressure of a finger and returns to its original position is behaving within its elastic range. If the finger presses too hard and leaves a permanent crease, the ruler has entered the plastic range. Structural engineering ensures that the building remains within its elastic range, even under the most severe winds expected over a design interval of 50 or 100 years. One critical requirement of this deformation is that it must leave no permanent trace. When calm weather returns, the building returns to its original alignment as though nothing had happened. But inside it, during the storm, a great deal has happened. The second layer is form. Wind does not act uniformly on a skyscraper. Above approximately 260 or 330 feet, average wind speeds increase rapidly with altitude. But average speed is not what affects the building most. The greater forces come from gusts, turbulence created by neighboring buildings, and a phenomenon that rarely enters popular conversation but dominates the desks of structural engineers: vortex shedding. When air encounters the vertical face of a building, it divides into two streams that flow around the sides. If the tower maintains a constant rectangular profile throughout its height, those streams separate alternately, creating small vortices that detach first from one side and then the other at a relatively steady rhythm. Each vortex pulls the tower laterally, in a direction perpendicular to the prevailing wind. A wind blowing from the east can make the top of the building oscillate north to south. It is like holding a hand outside the window of a moving car and feeling how small changes in angle alter the pressure. A uniform surface creates regular pulses. A varied surface disrupts the pattern. That is why the Burj Khalifa in Dubai, completed in 2010 at a height of 2,717 feet, uses a Y-shaped floor plan built around a system known as a buttressed core. Each of its three wings gradually narrows as it rises through 27 setbacks positioned at different heights on each wing. Structural engineer Bill Baker of Skidmore, Owings and Merrill designed this form specifically to prevent vortices from finding a continuous surface along the tower's 2,625-foot height. At every setback, the rhythm of vortex shedding changes. The wind can never organize its vortices into a sustained frequency. No dangerous amplitude can accumulate. The tower looks like a sculpture, and it is. It is also an aerodynamic device. What may appear to be aesthetic extravagance often conceals a purely technical solution. If the Burj Khalifa were a square column rising 2,725 feet, it would require far more structural mass to survive the winds of the Gulf. Its form saves steel. The third layer is invisible frequency. Every building possesses a natural frequency of vibration, determined by the combination of its height, mass, and distributed stiffness. Imagine a playground swing, and the principle becomes clear. A push delivered at the correct rhythm makes the swing rise higher and higher. A push delivered out of rhythm merely wastes energy. When periodic wind forces approach a building's natural frequency, movement can be amplified through a phenomenon known as resonance. That does not mean a single windy day will drive the tower into catastrophic resonance. Wind is irregular, and the structure possesses inherent damping, but the calculations must account for specific scenarios. A 1,312-foot skyscraper may have a natural oscillation frequency of approximately 0.1 to 0.15 Hz, meaning one complete cycle every 6 to 10 seconds. That is too slow for the eye to register easily, but fast enough for the human body to perceive through the vestibular system of the inner ear. There is a fundamental distinction that many people confuse. Displacement and acceleration are not the same thing. The top of a building may move 12 inches to one side over 10 seconds without anyone feeling much of anything. Someone walking across the upper floors might notice a subtle shift in the visual axis, but would probably not become dizzy. Another building might move only 4 inches, but complete that movement in 2 seconds, producing far greater acceleration. The body detects that acceleration. The inner ear reacts. Nausea follows. Then comes the sensation that the floor is moving away beneath the feet. Then comes the discomfort that convinces a tenant to leave the apartment and refuse to renew the lease. That is why the primary comfort criterion in modern skyscrapers is not measured in inches of displacement, but in milli-G, or thousandths of gravitational acceleration. Technical studies and recommendations suggest that residential towers maintain peak accelerations below approximately 15 milli-GE under annual winds, while office buildings may allow up to 25 milli-GE. The numbers are low, almost meaningless without context, but exceeding them can make a building practically unusable. The fourth layer is where the human being becomes an involuntary measuring instrument. A residential tower requires stricter criteria than an office building for the simple reason that its occupants are inside it at night. A person lying down can feel movements that someone standing up and distracted by work might never notice. A bed acts as an inertial reference. So does a glass of water on a bedside table. Hotels and residential towers also accommodate people who did not choose the building with any awareness of these risks. An office employee implicitly accepts that a commercial tower may sway during a typhoon. A hotel guest on the 20th floor does not know that the tower will behave like a flexible mast during the night. The comfort criterion is therefore a social decision disguised as a technical one. It answers an invisible question. How much movement would a vulnerable person lying in a bed they did not design tolerate before beginning to panic? One historical episode illustrates better than any engineering manual how skyscraper movement ceased to be merely a structural problem and became a human one. In 1977, New York City inaugurated the Citicorp Center, now known as 601 Lexington Avenue. The building rises 919 feet, contains 59 stories, and was designed by structural engineer William Le Mesurier. Because St. Peter's Church occupied one corner of the site, Le Mesurier had to support the entire tower on 4 enormous columns positioned at the midpoint of each facade rather than at the corners. The corners were cantilevered, projecting out over the church. To reduce wind-induced movement, the Citicorp Center became the first major skyscraper in the world to receive a tuned mass damper. It consisted of a 400-ton concrete block installed near the top of the building and mounted on a sliding system with springs and hydraulic dampers. It was designed to move in opposition to the tower, extracting part of the energy from its oscillation and reducing discomfort for occupants. In June 1978, Le Mesurier received a telephone call. A Princeton University architecture student named Diane Hartley, who was writing her thesis on tall towers, had noticed something strange while modeling the building. Under winds striking the building diagonally across its corners, known as quartering winds, the stress in the diagonal braces increased by 40% compared with the loading New York City's building code required engineers to calculate at the time. Le Mesurier repeated the calculations. He discovered that the building was indeed vulnerable. Worse still, during construction, some connections originally designed to be welded had been replaced with bolted connections, amplifying the problem. The engineer calculated that, without the tuned mass damper operating, a storm capable of bringing down the Citicorp Center would pass through New York approximately once every 16 years. With the damper operating, the probability dropped to approximately once every 55 years, but the damper depended on electricity. If strong winds caused a power failure, the device would stop working. Between August and October 1978, a team of welders worked consecutive nights inside the building, installing 2-inch steel plates over more than 200 bolted connections and converting them into welded joints. An emergency generator was installed to keep the damper operating during possible blackouts. The city secretly prepared an evacuation plan for the entire area surrounding the tower. No one living in Manhattan knew what was happening. The case remained secret until 1995, when an article in The New Yorker revealed it to the public. The Citicorp Center did not collapse, but it came dangerously close, and what saved it was the observation of a student who decided to check the calculations. The fifth layer of the problem involves the structure hidden inside the tower. A modern skyscraper is not a homogeneous column. It combines several subsystems. A rigid central core, usually made from high-strength concrete, contains elevators, stairways, and building services. Around that core, exterior columns rise vertically, connected by horizontal floor slabs and, in extremely tall buildings, by systems known as outriggers. Outriggers are horizontal structures that span entire mechanical floors, connecting the central core to the exterior columns. Imagine a mast anchored to the ground, with horizontal arms reaching out toward distant supports, and the principle becomes clear. By tying the core to the exterior columns, the outrigger makes a greater portion of the tower's width participate in resisting overturning. It is like widening the base without physically making it wider. The foundations also participate in the system. Wind acting at a height of 1,312 feet creates an enormous overturning moment that must be transferred into the ground through piles, pile caps, and, in many cases, combined raft foundations. The base of the Burj Khalifa, for example, rests on 194 board piles extending more than 164 feet into saturated sandy soil, requiring specialized calculations for behavior under cyclic loading. Every movement at the top begins at the facade and ends deep within the ground, passing invisibly through every structural element along the way. The sixth layer is the device that moves in the opposite direction. And this brings us back to Taipei 101, the building with the most famous tuned mass damper in the world. Completed on December 31st, 2004, at a height of 1,767 feet, the tower was built only 660 feet from an active fault line, on an island exposed to annual typhoons and frequent earthquakes. Between the 87th and 92nd floors, suspended from 92 steel cables measuring 3.5 inches in diameter and 138 feet in length, hangs a solid steel sphere 18 feet in diameter with a mass of 660 metric tons. It is the largest tuned mass installed in a skyscraper anywhere in the world and one of the few visible to the public, displayed as a tourist attraction inside the building's observation deck. When the wind pushes the tower in one direction, the sphere's inertia causes its response to lag, making it move in the opposite direction. 8 large hydraulic viscous dampers installed beneath the sphere convert the energy of that movement into heat, dissipating part of the oscillation. Under typical conditions, the system reduces the tower's sway by as much as 40%. The sphere can move up to 5 feet in any direction. Its greatest recorded displacement was approximately 3.3 feet during Typhoon Soudelor in August 2015. During the magnitude 7.4 earthquake that struck Taiwan on April 3, 2024, the building was also seen moving in a controlled manner without structural damage, while smaller neighboring structures partially collapsed. In addition to the main sphere, 2 smaller dampers weighing 7 tons each are installed near the tip of the ornamental spire, protecting the pinnacle from localized vortex shedding. The sphere does not support the building. If it were removed, the tower would not collapse. But during typhoons, its occupants would experience far greater discomfort, probably intolerable in a residential building. The technical irony of the system is that, to reduce the tower's sway, the damper itself must sway. The sphere inside Taipei 101 moves constantly. It is the most visible part of the system, and it appears to be doing exactly what it was designed to prevent. But the secret lies in the delay. By moving slightly out of phase with the tower and creating an opposing force while the building is accelerating, the device pulls the structure back. It is like 2 people pushing a swing at different rhythms. One accelerates it, the other slows it down. The result is a smaller oscillation amplitude. Viscous dampers, tuned liquid tanks, computer-controlled active counterweights, and semi-active systems that adjust their response in real time, All of these variations exist today. It is not true that every skyscraper contains a giant sphere. Many use pairs of viscous dampers concealed inside mechanical floors. Some, such as 432 Park Avenue in New York City, which rises 1,396 feet, use two 650-ton concrete dampers hidden on the upper floors. Visitors never see them. The body, however, senses their absence, or rather, it senses the movement they prevented. Return to the opening scene. The glass of water moving on the 89th floor of Taipei 101 during Typhoon Soudelor. The light fixture suspended from a thin cable tracing a small arc. People walking through the rain on the street 1,640 feet below, unaware that the tower above them is temporarily leaning away from its original axis. That image should no longer appear dangerous. It is the result of a design decision made years before the first column was cast. Materials that deform elastically and return to their original shape. A sculptural form that disrupts the wind before it can organize its pressure. A concrete core that distributes the vertical load. Exterior columns connected by outriggers to widen the tower's effective base. Deep foundations that transfer the overturning moment into the ground. And a golden sphere suspended from 92 steel cables inside the tower, moving slightly out of rhythm with the building to remove a portion of its motion. The skyscraper does not remain standing despite swaying. Under certain conditions, it remains standing because it has been allowed to sway within carefully defined limits. True stability is not the absence of movement. It is knowing how far something can yield without losing its balance. Subscribe and turn on notifications for more stories hidden behind the structures that define the skylines of our city montañas.